recording here. Okay, so recording has started. So we are continuing our discussion of antiderivatives. And antiderivatives are gonna are really when we're computing an antiderivative, we're finding what's called an integral, and that's what we're going to get into in Chapter 5, integration. An antiderivative, okay, the definition of an antiderivative here is that a function, and you know, they use different notations, but capital F, a function capital F, is an antiderivative of a regular function f on an interval I if the derivative of the antiderivative function equals the function. So the derivative of f of x equals little f of x for all x in the interval. And they talk about, like, well, what would a general antiderivative be? A general antiderivative is going to have a constant c after it. Okay, a constant c after it. So like for instance, in this little example here, I'll just highlight this part here. If you have a function f of x equals x squared, it's easy to see that the antiderivative would be capital F of x equals 1/3 x cubed, because if you differentiate 1/3 x cubed, you're going to get x squared. Okay, but the thing is, if you had a function g of x which equaled 1/3 x cubed plus 100, that also, the derivative of that g of x function also equals x squared. So both functions, capital F and capital G, are antiderivatives of our function f. Indeed, any function of the form h of x equals 1/3 x cubed plus c, where c is a constant, would be an antiderivative of your function. Okay, and so the general antiderivative has this constant c, which we're going to be calling it a constant of integration. And they have a picture here in figure 1, members of the family of antiderivatives of this function. And they're drawing all these functions, which are all antiderivatives of f of x equals x squared. So that's just a little bit of an introduction into this. And you know, in example 1, they say, well, let's find the most general antiderivative of the following functions. And they have the sine of x, 1 over for a, b is f of x equals 1 over x, and c is f of x equals x to the nth power. Okay, so for a, the antiderivative of the sine is minus cosine. Because if you take the derivative of the minus cosine, well, you're going to get -1 times negative sine of x, which is the sine of x. So the negative cosine of x is equal to the sine of x. And therefore, the antiderivative is, the general antiderivative would be negative cosine of x plus c. Okay, is that, are there any questions on that? So what you're doing is you're going backwards, basically. You're used to taking a derivative of a function. Now you're going from the derivative back to the original function that you took the derivative of. It's like going backwards. It's exactly like going backwards. If, for instance, the f of x equals 1 over x, part b, well, the derivative of the log of x is 1 over x, right? That's one of those derivative facts that you've learned. And so therefore, the general antiderivative of 1 over x is the log of x plus c. Okay, the log of x plus c. However, we have to be a little careful because the antiderivative really of, well, I want to be careful here. The general antiderivative of 1 over x is really the log of the absolute value of x plus c. Okay, that's true on any interval that doesn't contain 0. Okay, but I don't want to get, you know, caught up in you know, too many details. But we know that well, let me see here. I'm trying to think if there's anything sort of intuitive that I can offer you here. You learned back in chapter 3, I believe it was chapter 3. Just double check here. Hold on. You learned derivative rules in chapter 3. And let's see here. I'm just finding the right section, class. Yeah, if you look in section 3.7, example 6, section 3.7, example 6, they established that the derivative of the log of the absolute value of x equals 1 over x. And therefore, the general antiderivative of 1 over x is equal to the log of the absolute value of x plus a constant. So that, you have to be careful with that, because a lot of times students, like in calculus 2, they'll forget to have that absolute value around the x, and you have to have it there. Okay, so there's another antiderivative. And now for C, well, are there any questions so far? Okay. All right. Well, now for C, we want the antiderivative of x to the nth power. The antiderivative of x to the nth power, the general antiderivative, would be x to the n plus first over n plus 1 plus a constant. Okay, that would be, because if you differentiate that function, you'll get x to the nth power. Okay, and it's valid for n greater than or equal to 0. So again, what you're doing is you know how to take derivatives of functions, but now you go, so you can move forward. Given a function, you can take the derivative. Okay, can you, given a derivative, then go backwards and get the function whose derivative it is? Okay, and they have here a table of anti-differentiation formulas. This is a table 2, and they give some different functions in table 2, along with some different antiderivatives. Okay, and so and you really need to learn these antiderivatives well, because it's going to become very important. Well, it's important, of course, in calculus 1, but then in calculus 2, you're going to be doing integration techniques like substitution and integration by parts and so forth, and you're going to have to know your antiderivative rules very well. Okay, you're going to have to really know them well. So if there are no questions, let's go ahead and look at a few examples. Okay, are there any questions at all? Okay, Joe's good. Okay, Nicholas is good. Very good. All right, and again, I always pause a little bit if it were in a class. Well, you know, it's always good to pause to see if there are questions. And new people, new instructors tend to make the mistake of not pausing long enough, you know. But hopefully I don't make that mistake. All right. On that note, let me bring up an example. We're going to look at 3 of them here. Okay, let me give you a moment to copy this example down for section 4.9. This actually should be, sorry class, it should be section 4.8 here. So let me fix that. Section 4.8. Okay. All right, I'll let you copy that down. Okay, so here in this problem, we want to find a function f whose derivative, f prime of x, is equal to e to the x plus 20 times 1 plus x squared to the negative first. And in addition, for this, we're going to be given what's called an initial value. We're going to be told that when x equals 0, the function equals -2. Okay, so by the general antiderivatives always have those constant c's with them. You know, you'll see this. But if we specify an initial condition, we can solve for that constant. So let me show you how to go about this problem. All right. First of all, what I'm going to do is I'm going to write the 1 plus x squared to the negative first as 1 over 1 plus x squared. That's something, you know, I'm a little more, and there's a reason for that, because you'll see that. But certainly I can write my derivative f prime of x this way. And now I'm getting my original function. The original function f is the antiderivative This is the antiderivative of, I'll put it over here. Hold on. Antiderivative of f prime of x. Okay. So what you're used to seeing, is this, like in the notation, some of the notation you've seen already in the book says that if you take the derivative of the antiderivative, one moment here, hold on. Yeah, that'll give you your original little function f back. Okay. Let me just see here. One moment, class. I'm just trying to, this may be, let me just see, one moment here. Yeah, so, but the point is that I don't want to get caught up too much in notation. This function f of x, if you were to differentiate this function f of x here, this little function f of x, you would get back f prime of x above, because the derivative of e to the x is e to the x. The derivative of the arctangent of x is 1 over 1 plus x squared. The derivative of a constant is equal to what? What's the derivative of a constant? 0. That's right, Ian. That's right, Betsua. So do you see? That's right, John. So do you see that if we just, like, you know, used our derivative rules, I don't want to get too complicated, but if we just used our derivative rules here, just clear this out. If we just use our derivative rules to differentiate this function f here, do you agree that we would get the derivative above? Okay, who agrees with that? Who? Yeah. That means then, good, that means you found the antiderivative. You found the antiderivative, and here it is. But this is what's called a general antiderivative, because you have a constant here. So, like, for instance, in WebAssign for like Friday's homework, when you find a general antiderivative, you have to remember your constant C of integration. And it's usually a capital C, by the way. WebAssign's a little picky on that. If you put a lowercase c, it might not accept it. It probably wants a capital C. But in this case, we're given more information than just what the derivative was of our function. We were also told that f of 0 equals -2. And so we can use that piece of information to solve for this constant. Okay, we can use that piece of information to solve for that constant because, okay, so the idea is that if we're looking for a function with a certain antiderivative, there are a lot of functions that have that. No, I want to be careful. If we're looking for a general antiderivative, I mean, there are a lot of antiderivatives to f prime of x equals e to the x plus 20 times 1 over 1 plus x squared. There are a lot of antiderivatives, and they all differ by a constant. What I mean is every antiderivative will have a different constant. So that creates a family of antiderivatives and a family of functions that you can graph, just like the picture you saw in Figure 1 on in section 4.8. We could graph this family here. We could graph this family of antiderivatives. But if you also specify a coordinate, okay, you're saying that when x is 0, the function equals -2. So this particular antiderivative function also has to pass through the point 0, -2. When you do that, then you can uniquely solve you can find a value for the constant. In other words, there's only one function, only one antiderivative only one antiderivative, there's only one antiderivative function that's going to pass through the point 0, -2. And so what you do, you should say, okay, well, f of 0 is equal to -2. Let me put x equals 0 in my antiderivative formula here, as you see. So like the x, I replace that with 0. The x here with the arctangent, that gets replaced by 0. Okay, and I will get this equation. -e to the 0 is 1. The arctangent of 0 is 0 because the tangent of 0 equals 0, so the arctangent of 0 is 0. So this allows me to solve for my constant, and the constant will equal -3. And so that means then that the function that the antiderivative that I am looking for is f of x equals e to the x plus 20 times the arctangent of x minus 3. Okay, and please let me know if you have any questions. So when you get antiderivatives, you're going backwards. It's the opposite of taking derivatives. It's anti-differentiation. You're used to differentiation. Now you're doing anti-differentiation. But it should be pretty simple. I mean, if you're able to walk down the street in one direction, can't you walk back up the street in the other direction? Right? Isn't that usually? Yeah. So that's how I kind of think of it, Rodrigo. I like to use analogies. Okay, I like to use analogies. Okay. And there are reasons why we would want to find an antiderivative. We'll see in a very applied problem coming up here. But if we're good on this, let's go to the next example. Are there any questions on this example? All right. If not, let's go to the next example. Okay, now here you have the second derivative function of t. Okay, let me give you a moment to copy that down. Okay, so here we want to find the function f of t, but instead of giving the first derivative of the function, we're given the second derivative of the function. Okay, we're given the second derivative. This is interesting. And we're given two conditions on the function. So let me ask you, can we go directly from the second derivative in one step and figure out what the function f is? I mean, the last problem, we were able to determine the function in one step by doing one antiderivative. Is that going to hold true for this problem? Can we go from knowing the second derivative of our function and then to just in one step, one antiderivative knowing the function? Sebastian doesn't think so. Well, how many steps do you think this is going to take? That's right, John. Very good. Because the antiderivative, what would the antiderivative of the of f the second derivative f prime of t, what would the antiderivative be? I'm sorry, f double prime of t. What would the antiderivative be for the second derivative? What I mean is, yeah, that's what I'm looking for, Sebastian. It would be f prime of t. Okay, it would be f prime of t. And then you got to take the antiderivative of f prime of t to get to f of t. So this problem is going to take two steps. It's going to take two steps. All right, are there any questions on that? Okay, so sometimes, you know, before you just kind of charge into a problem, you know, to work on it, you want to think a little bit before you just, you know, charge into the problem. And you know, we have a plan now. We have a plan. So let's go ahead and start looking at the solution. All right, so the general antiderivative of my second derivative will be the first derivative. So the antiderivative of 2e to the t is just 2e to the t. And the antiderivative of the sine of t is minus the cosine of t. And then you have the constant. Okay, there shouldn't be a period there. Okay, so this is like, again, it's like going backwards. You're used to going forwards. You have the function, you find its derivative. Now you're being given a derivative and you have to find the function. So you're going backwards. Okay, are there any questions up to here? All right. The no, the antiderivative of the cosine. Well, hold on. Good question. So the derivative. Hold on. One moment. Good question. Let me. So we're up to here. Let me just write. Hold on. This is. All right. So the derivative. Derivative of the sine of t. What's the derivative of the sine, class? Good. That's right, Nicholas. That's right, John and Betsua. That's right. Derivative of the sine is the cosine of t. Okay. That's one fact. Okay. Hold on here. One moment, class. Okay. But you have to just give me a moment. All right. Now let's also write down separately here the derivative of the cosine of t. What's the derivative of the cosine of t? Minus the sine. Good. Good. Okay, so in going from, I mean, the derivative of we're saying the antiderivative of the sine is minus the cosine, right? That's what we're saying. So which formula here, formula 1 or formula 2 in the boxes here, which formula is the one that's going to be helping me? The first formula here or the second formula? Which is the formula that's going to help me in finding the antiderivative of the sine of t? Well, let me add a little bit more here. Hold on. We know the derivative of the cosine is minus the sine. So then what is the derivative of minus the cosine? That would just be the sine. Good. Very good. Because it's like multiplying the negative sine of t here by -1, right? Let me see here. Let me put in an additional step here. Hold on. This is the kind of thing that takes, if I were in a classroom, I'd write this on the board like in a few seconds. But here it takes a little more time. But that's okay. Okay. So spring will be online, John. Wait, John, hold on. For classes in the spring, I believe if there are the first half of the semester, the classes are going to be at least most of them are going to be online for the first half of the semester. Second half of the semester, some classes will be on campus, but there will be, I think, others online. But we'll one moment here. One moment. We can talk about that. But let me just. Wish I had a little more room here. All right, let me erase. I do what I have to do, right? So what I'm trying to do is I'm trying to justify why the antiderivative of the sine is equal to the minus cosine of t. And we know that the, sorry, hold on, one moment. Okay, we know that the derivative of the cosine of t is equal to minus the sine of t. So then the derivative of minus cosine of t should equal minus the derivative of the cosine of t. Okay, which would be which would be then minus sine of t. Hence, you're going to get a positive sine of t. Okay, and so it's this rule here that, I mean, the first rule, sure, the derivative of the cosine of t is negative sine of t. Okay, but remember, we don't have negative sine of t here. We have just the positive sine of t. Well, it's intuitive then that if the derivative of the cosine of t equals negative sine of t, the derivative of, we're only off by negative, right? So the derivative of negative cosine of t, the negative 1 can be brought out in front of the derivative. So that's going to be negative, negative 1 times negative sine of t, which gives you a positive sine of t. Hence, the antiderivative of the sine of t is negative cosine of t. Does that make sense? Does that make sense? Okay, but Sue is comfortable. Good. All right, so, you just manipulate the rules a little bit. All right, well, we're down to f prime of t, but now I need to get f of t. So I'm going to now then take the general antiderivative of f prime of t. Okay, and so the antiderivative of 2e to the t is just 2e to the t. Okay, that's right here. The antiderivative of 3 cosine of t is just 3 times the sine of t, which is right there. The antiderivative of this constant c is just c times t. And then we have to add a constant, so we add a plus d. Okay, and this is the general antiderivative. You notice that the constant that we add, the d here, we don't add like another c. We use a different letter because we don't want to assume that constant d is the same as that constant c. They could be the same, but they could be different too. So you need to use a different letter. Okay, that's important in your work. Well, all right. So now, well, are there any questions up to here? All right, well, if there are not, now what we have to do is we have to solve for C and D. Now, what will happen is in WebAssign, if they said find the general antiderivative, then this would be your answer, okay? This would be your answer. But we're told in this problem that we're given 2 conditions about the function. Okay, we're told that when x equals 0, the function equals 0. So I can substitute in 0 wherever the t is in my function f, as I do here, and that's going to allow me to solve for d, and d will equal negative 2. All right, please let me know if you have any questions. All right, may I go to the next page then? All right, I'll go to the next page if there are no questions. So now we have that d equals -2. Okay, we have that. And so this is our function. F of t equals 2 times e to the t minus 3 times the sine of t plus c of t minus 2. But we're not done yet because we're given another piece of information. We're told that when t is equal to pi, f of pi is equal to 0. So I can substitute in 0 again for t. Here. And I do this so I can solve for c. See, if you have two unknown constants, a c and a d, you need two pieces of information to uniquely solve for those constants. If you have just one unknown constant, you only need one piece of information to solve for the unknown constant. Yeah, it is interesting. It is interesting, Nicholas. Sure. Well, all right. So we solve for the constant, and we'll find out that the constant equals 2 minus 2 times e to the pith power divided by pi. You can get some very interesting constants. Okay, let me know if there are any questions. Okay, let me see here. Yes, Betsua, it is. It really is interesting. I agree. Okay, well, then our function is going to be equal then, the function we're looking for that meets the conditions in the problem. You know, we were given what the second derivative was of the function, and we were given two conditions about the function. Those are actually called, in this case, boundary conditions. But that's fine. But we were given two conditions. And f of t is equal to 2 times e to the t minus 3 times the sine of t plus the quantity 2 minus 2e to the pi power divided by pi times t minus 2. Do you think WebAssign is going to want this exact value here in front of the t, or do you think it'll want an approximation? What's WebAssign going to want? Should we approximate this constant? That's right, Sebastian. Definitely not. I mean, you know, we have the exact value. The exact value is best, right? Okay. Well, are there any questions before we move to our next example? Okay, Nicholas is good. It's always good. Okay. All right. Does anybody need more time to copy, or are we good? Okay. All right. Well, so yes, Yaki. The page before, yes, yes. Okay. All right. You're good. All right. Okay. Well, so these are interesting problems, and there are some very important applications. For instance, as like in the intro to section 4.8, they mentioned that a physicist who knows the velocity of a particle might wish to know its position at a given time. Okay, that's a very nice example. And what I'm going to do is I'm going to do an example here, a very applied example. So there's going to be a little bit of copying for you to do for this example, but I want to do an example where we do a lot of things, so it helps you out in the homework. Okay, so how many have heard of so this is our applied example, a good, nice applied example. How many have heard of the CN Tower located in Toronto, in Ontario, Canada? How many have heard of the CN Tower? Okay, Nicholas has. Yeah, I mean, you can just Google it. It's 450 meters above the ground. Okay, so that's pretty high. Okay, that's pretty tall. All right, let me give you a moment to copy this example down. Okay, and then we'll go over this. Give you a few more moments here to copy this down. Okay, so in this problem, we're told that a stone is dropped from the upper observatory. A stone is dropped from the upper observation deck, the space deck of the CN Tower, which is 450 meters above the ground. Okay, 450 meters above the ground. And, well, part A, we want to find the distance of the stone above the ground level at time t. How many think that's just kind of interest to find? Part A. Sure. I mean, that's of interest, of course. Part B, how long does it take the stone to reach the ground? With what velocity does the stone strike the ground? Okay, do those sound like interesting questions too? Okay. All right. I mean, I think I'm interested. I'm curious. Okay. And Nicholas and Betsu, I assume you are too for part B. Okay, wonderful, wonderful. And then in part C, so like for parts A and B, for this part here, A and B, you're just dropping the stone, okay? You're not like tossing it downward, throwing it downward. You're just dropping it from rest. But in part C, the stone is going to be thrown downward at a speed of 5 meters per second, and then we want to know how long does it take to reach the ground. Okay, how long does it take to reach the ground? And, you know, intuitively speaking here, just one moment. One moment. You know, we would think that if we were to throw the stone downward, then the stone should reach the ground in less time than if we were to just drop the stone. Okay, so I mean, what do we need to, I mean, like now going back to part A, we're just, you know, dropping the stone from rest and watching it go down. I mean, what are we going to need here? What are we missing in this problem that we had in the previous two problems? What are we missing? An equation. That's right, Ian. An equation. All right. Well, so we have to come up with an equation, right? And let me show you how this works. Okay, so may I go to the next page? Are we good? All right, let's go to the next page. So what I'm going to do is the motion is vertical here now for this stone. It's not like you know, a particle moving sideways and then, you know, to the left and the right. The motion's vertical. So like for a particle moving sideways, when a particle moves to the right, that's positive velocity. When the particle moves to the left, that's negative velocity. Well, since the motion of the stone is strictly vertical, we're going to choose positive direction to be upward direction, and then therefore downward direction would be negative. So we're going to define, first of all, S of t, and you've seen this before with like the particles when you studied particle motion. S of t is going to be the distance the stone is above the ground. What I mean is the notation S of t you've seen before. In this case, S of t is going to be the distance in meters, and we use M for meters, that the stone is above ground at time t. I should say above the ground. Above the ground at time t. Okay. But that's fine. That's fine. So S of t is, once again, it is the distance in meters that the stone is above the ground at time t. And t, of course, is in seconds. It's important that we you know, denote our units. And let me just add the word the here. It just sounds better. Okay. On the other hand, velocity in this case is going to be, therefore, it's got to be in meters per second, and that's just the velocity of the stone at time t. Okay, so given this, we'll note that at time t, the distance S of t, which is the distance that the stone is above the ground, that's decreasing, and velocity is also decreasing as well. It's getting more negative, right? It's getting more negative. So I want to be a little bit careful here. One moment. I want to be careful on that statement. I don't want to say getting more negative. No, what I mean is, since we're defining positive direction to be upward and negative direction to be downward, since the stone's going downward, the velocity is negative. It's just the same kind of thing with like when you studied the particles. When the particle was moving to the right, that was positive direction, the velocity was positive. When the particle was moving to the left, that's in the negative direction, so the velocity was negative. So it's that simple. Velocity is decreasing. So acceleration is going to be negative. Okay, acceleration is going to be negative. Since velocity, well, yeah, the acceleration is going to be negative because acceleration is the derivative of velocity. And since your velocity is negative, your acceleration is going to be negative. I want to be a little bit careful here. I want to be a little bit careful what I say. Let me rephrase that. Hold on. Everything I said was okay, but the velocity is decreasing. The velocity is decreasing because the stone is going to be I want to say this the right way. As time increases and the stone's falling, is the stone going to be picking up speed, or is it going to be decreasing in speed as the stone's dropping from the tower? It's getting faster. The stone's picking up speed, so the velocity is decreasing. That's what I'm trying to say. Okay, but the values of the velocity are negative because the stone's going downward. But the fact is, because the stone is picking up speed, indeed, the velocity is decreasing. And that means then the acceleration is going to be negative. Now, in terms of, this negative 9.8, where do I get that from? I just said, okay, the acceleration, which is the derivative of velocity, is equal to negative 9.8 meters per second squared. Oh, where's the 9.8 come from? Where's the negative 9.8 come from? What's that? Why did I pick that number? Good, Ian. Good, Ian. That's acceleration due to gravity. Okay. That's right, Nicholas. We are not assuming horizontal motion of the stone. It's strictly vertical motion. That's correct. And I'll note here that if the units were in feet, if we were dealing with this problem, where instead units are in feet, then the acceleration would be negative 32 feet per second squared. So they do a problem in example 6 that they deal with a ball being thrown off the edge of a cliff. And in that problem, the units are in feet. And so example 6 in the text is another problem similar to this one, but they're using different units. And you'll need to look at example 6 in the textbook to help you with some of your homework. But this problem here will help you with other parts of your homework. So this here was just a note, so you're aware of it. Okay, so now we have an equation. Acceleration function. Acceleration at time t equals negative 9.8 meters per second squared. Okay, what are we going to do with our acceleration function? I mean, what we're looking for in this problem is we're looking for the distance. Distance is s of t. So that's right, Ian. We're going to take the antiderivative of acceleration. And what would that give us? If we took the antiderivative of acceleration, would that give us the distance? Would that give us s of t? What's the antiderivative of acceleration? Well, okay, but what it gives us, that's right, Nicholas, it gives us velocity. Okay, so if we do we can only do antiderivatives one at a time. Let me go to the next page if we're good. So the antiderivative of acceleration is velocity, and that's going to be negative 0.98 t plus the constant. You cannot forget the constant. So what we want to do is we want to solve for that constant. Well, we're told that the stone was dropped from rest initially. Okay, so at time 0, the stone is dropped from rest. So that means the velocity at time 0 equals 0. And you can show that the constant then, that constant c equals 0. And so your velocity function is negative 9.8 times t. Now I want to make sure I'm pacing myself well, I should say. So let me know if you have any questions. Okay, well, now we want to determine what the distance is for the stone, the distance that the stone is above the ground. That's S of t. Now S of t is also position. Okay, S of t is the position of the stone. If you know the position of the stone above the ground, that's the same as the distance that the stone is above the ground. Okay, so we have to then, to get the position or distance S of t, we have to find the antiderivative of velocity. And again, you're going to get another constant d here, constant of integration we call it. Notice I don't use c again here, I use d. And that's going to be important on your exam when you show your work. I'm going to look for stuff like that. Okay, because believe me, it does make a difference. It does make a difference. Okay, so S of t equals negative 4.9 t squared plus d. That's what S of t equals. I want to find what d is. I can't, the formula is not useful to me unless with these unknown constants in there. In order for me to like do part B, like when does the stone reach the ground, that kind of question, at what time does the stone reach the ground, I can't have a D, an unknown constant in there. So is there some piece of information that we're told about the stone, its position in the problem? If you go back to the reading the problem, is there some piece of information that they gave us? Good, John. It's dropped from 450 meters. So initially the stone, at time 0, initially the stone is 450 meters above the ground. And so that means then that we can, we can solve then for D. Because the position of the stone, the distance of the stone is above the ground initially. At time 0, it's 450 meters. So we just then plug in 0 for t in our S of t function, and we'll determine that d equals 450. Okay, so think for a moment. Let's see here. So Zoe asks, is that calculation necessary when the problem gives you the 450? I know what you're saying. In like a physics class, they might not like worry about that. But in our class, it is necessary to do this calculation. How many maybe have seen this kind of problem in a maybe Physics 1 or a class they're taking? Okay, Zoe's seen it, and calculus is, all of these, physics derives from calculus. The physics derives from calculus. So, like for instance, well, yeah, you'll see in calculus too, work problems. For instance, work problems are done in physics, but they can be derived based on calculus ideas. So we want to use our calculus ideas, and not so. All right, good question, Zoe. Now that 450 equals D, I'll go to the next page if that's okay. Okay, well then, now S of t is going to equal negative 4.9 t squared plus 450. And I can equivalently write S of t as 450 minus 4.9 times t squared. I can equivalently write S of t that way. And I like writing it that way because as t increases, it's easy to see when t is 0, S of t is 450. And then as time goes on, S of t decreases because of the negative 4.9 t squared. It just kind of makes intuitive sense for me to write S of t this way, having the 450 first, and then minus 4.9 t squared. How many kind of like it in this form as well, the second form? Okay, Joe likes it that way. Yaki, very good, very good. All right, well now we've determined our position of this stone. I mean, it's absolutely amazing, absolutely amazing. We've determined the position, S of t, of this stone, the distance that the stone is above the ground at time t. So of course, when does the stone hit the ground? When does the stone hit the ground? Well, that's what we're doing in part B. We want to find the time when the stone hits the ground. Okay, whenever they say when, they're talking about find the time. Well, the stone hits the ground when S of t is equal to 0. Okay, that means you're 0 feet above the ground. So S of t equals 0, you just set 0 equal to, well, you just, set your S of t equal to 0 and solve for t. And when you do that, you're going to get 4.9 t squared equals 450, which means t squared is 450 over 4.9. And to get the time t, you take the square root. Now normally, well, so t squared is 450 over 4.9. When we take the square root of both sides, technically t should equal plus or minus, right? The square root of 450 over 4.9. But time is positive here. Time has to be positive because it's initially we dropped the stone. That's at time equals 0. And so time is increasing, and you can't go backwards in time, right? You have to go forwards in time. I mean, well, what I mean is in this problem, we're going forwards in time. So we're going to take the positive square root. And so this is the exact answer. And then you can round that to 2 decimal places and you get 9.58 seconds. So WebAssign will tell you when to round your answer to the nearest decimal. But that's going to be the time when the stone reaches the ground, 9.58 seconds. So if somebody drops a stone and you're from the tower and you're at the bottom there, you have 9.58 seconds to get out of the way, right? Actually, get out of the way a little before then, right? But, you do have to be careful. I remember I was at when I was a kid, I went to the Empire State Building. And I noticed at the base of the Empire State Building there were some pennies, and the pennies were like embedded in the concrete, you know. So somebody must have dropped a penny from the top of the Empire State Building, and it went into the ground below, you know, dropped, and then when it hit the ground, it kind of went into the ground a little bit. So, you know, this problem reminds me of that. All right, are there any questions? Are there any questions so far? All right, well, part C of the problem says if the stone is thrown downward, with a speed of 5 meters per second, how long does it take to reach the ground? Okay, how long does it take to reach the ground? Okay, so for part C, for that part C, and I'll go to the solution here, the stone is initially thrown downward with a speed of 5 meters per second. That means then that the velocity at time 0 equals -5. So you don't have to start right from the acceleration. You can go right from the velocity function, which you derived in part B. The velocity function was negative 9.8 t plus plus a constant c. But since your initial condition is different now, you know, your initial condition isn't that initially the velocity is 0. Since you're throwing the stone downward at 5 meters per second, then your initial condition there is velocity at time 0 is -5. And you solve for c, you're going to get -5. And so you get a different velocity function. Your velocity function in this case is negative 9.8 t minus 5. I mean, the velocity function would have to be different if you're throwing the stone down initially, as opposed to, you know, just dropping the stone. Of course, the velocity is going to be different. And that's reflected in the different velocity function that you have here. V of t equals negative 9.8 t minus 5. Okay, are there any questions? Well, the rest of the problem is just similar to what you did in part B. You have to find your new position function, your new distance function, s of t. Well, you're going to take then the antiderivative of your velocity, okay, and of course the antiderivative of -5 is -5t, and now you have the constant d that you have to solve for. Okay, so s of t will equal -4.9 t squared minus 5t plus d. And you're going to have to solve for d. It's really a beautiful problem. It really is. Well, again, the initial condition is that on distance, initially the stone is 450 meters above the ground, because you're dropping it from 450 meters above the ground on the tower. And so if you then substitute in 0 for t, as you see it here, you solve for d, and d is 450, and you'll get your new position function. which obviously is a little different. So really, we're deriving these distance formulas, the distance that the stone is above the ground. We're deriving the distance or position formula from fundamental principles using calculus. There's always a reason why things are true. In pre-calculus, how many remember maybe seeing distance function, like distance functions s of t, maybe similar to this in pre-calculus? Okay, Nicholas remembers seeing it, and you know, you were just given the function, right? You were given the function and you worked with the function. But now you can actually derive the function using calculus. You know how that function's derived. Okay, which is a very nice thing. Okay, so now what we want to do, remember, for this part C of the problem, we want to know how long does it take for the stone to reach the ground. So what do we have to set S of t equal to? We have to set S of t equal to well, when the stone reaches the ground, it's 0 feet above the ground. That's right. Let me just check one thing here, by the way, class, on my thing. Yep, we're good. Okay. Right. So we're going to set then, we're going to set S of t equal to 0, which we do here. And we have to solve for t. So I have a quadratic equation here. Negative 4.9t squared minus 5t plus 450 equals 0. And here I'm solving for t. Man, what am I using here? T equals all this to the right. What did I use there? What special formula was used? The quadratic formula. Good. Good. Okay, we're using the quadratic formula. So you remember t equals negative b plus or minus the square root of what goes under the radical there. Right, good, Betsua. B squared minus 4ac. Okay, one moment, I see a question there, but let me just, b squared minus 4ac, all divided by what? All divided by 2a. Good, Zoe. Good, Trevor. So, of course, in our problem, the negative 4.9 is the A. The negative 5 is the B. And the positive 450 is the C. Positive 450, right? So, hold on here. Okay, let me see. Well, yeah, Ian, let's see. Let's see on that. So you're going to get t equals -5 plus or minus the square root of 8,845 divided by -9.8. Okay, and but we're going to choose the minus. Now notice we had plus or minus here. We had plus or minus here, but we chose the minus. Why did we do that? Why did we choose the minus when we solved for time t? Good, good, Zoe. Time is positive. If we had used the plus part in the, here, if we used the plus part, we would have time being negative, and time is positive. So we have to choose the negative. And you will get 9. This is the exact answer. And you might have to type in that exact answer in WebAssign, but unless it says round to 2 decimal places or something. Rounded to 2 decimal places, it's going to take 9.09 seconds for that stone to reach the ground if we initially threw it downward at 5 meters per second. And Ian makes an interesting point. It's only like half a second faster. It only takes half a second faster to reach the ground. I mean, well, if we just drop the stone, it takes approximately 9.58 seconds to reach the ground. But if we throw the stone downward at 5 meters per second, the stone will reach the ground in about half a second less time. Well, it is interesting, Ian. It shows you the power of acceleration. Acceleration really plays a huge role in the velocity of that. Acceleration due to gravity plays a huge role in the velocity for this stone. Okay, one moment. All right, so are there any questions at all on this? Okay, let me stop the recording.